Hey guys, I'm going to do a lesson on waves and sound. So let's kind of run through that. So we're looking at chapter 25 and chapter 26, waves being chapter 25 and sound being chapter 6. And I'm going to do both of those two things together. Here you have actually a close-up image of some guitar strings. And then in fact, if you could look real closely at the guitar strings, they actually might look like this at any given point in time. They actually will have that sort of wave look to them. It happens so fast your eye can't see it though. So here's the parts of a wave. A wave is going to be, no matter what type of wave and what it actually does, we're going to draw it or represent it in this sort of sinusoidal wave kind of structure here. So a wave is going to go up and down relative to this midline, so what I'll call this, and the distance between this point and this point here is the wavelength. It's measured in meters. These high points are known as peaks or crests. The low points are known as troughs, and the distance between the midline and a peak, or the midline and a trough, and that's called the amplitude. Do not confuse that with wave height. Okay, the wave height would be the distance between the very top and the very bottom. And in physics, we don't really care about that. That would be for a surfer, right? They care about that. For a water wave, they would care about the difference in that height. But what we care about is the energy necessary to displace it from where it would be otherwise, which is where the midline is, to displacing it to its peak or trough. So that's the amplitude. And when this thing goes through one complete cycle, okay, it has gone through one wavelength in one complete cycle. So if you see it's at the midline on its way up, and it comes back down, and then it's crossed in the middle on its way up, and at that point it's gone through one complete cycle. Okay, so you should know the parts of a wave. The period of a wave is going to be represented by a capital T. It is measured in seconds, and it is the time it takes for one complete cycle of a wave, or any sort of repeating sort of cyclical sort of thing. That's the big T, measured in seconds. Frequency is has an inverse relationship. In fact, it's the reciprocal to period. Frequency is how many times per second this cycle repeats. It is measured in cycles per second, otherwise known as hertz. So if it's 10 beats per second, it might be like in fact, that's probably not even fast enough to represent 10 hertz. But regardless, if I were to clap 10 times per second, then that would be a frequency of 10 hertz. So F is 1 over T, and T is 1 over S. T is 1 over F. I don't know my letters anymore. And so they are reciprocals of each other. There's a couple of different types of waves. First, we have transverse waves. Transverse waves are waves that cause particles to vibrate perpendicular to the direction of motion of the wave itself. So if you notice, the wave itself is moving left to right. But if you were to pick out any particular particle, any individual particle is just moving up and down. So they are perpendicular to each other. That is a transverse wave. This is fairly typical of what people think of in terms of waves. Alternatively, there is longitudinal waves. A longitudinal wave is one in which the particles move parallel or in the same direction as the wave itself, and so that would be represented here. This would be like sound, where there's some sort of diaphragm moving back and forth, and it causes these particles to move back and forth. These are the compressions here, or the wave fronts, and then in between the two, you have what's known as a rarefaction. It is less pressure, or less molecules within that space. So you have compressions, okay, and then in between them you have rarefactions, and they will propagate away from the source. So going back, we have these transverse waves where the particles move side to side compared to the wave itself. An example of a transverse wave would be light or any sort of electromagnetic radiation. So that'd be light, that'd be gamma rays, X-rays, ultraviolet, visible, infrared, and radio waves, and of course visible light in there as well. And so all of those would be transverse waves. Longitudinal waves would be something like sound, and then you have other waves that could be either longitudinal or transverse. Water waves are actually neither. It's a kind of a combination of the two. which we're not going to talk about too much, but I figured I'd kind of talk about it for a quick second. And any particle in any water particle is going to actually move in essentially a perfectly circular path. The farther you go down on the water column, the smaller that circle is. And so if you were to watch a duck on the surface of water and as a wave goes by, that duck is actually going to move in a perfect circle, which if you've ever watched, it's next time you're ever at a pond and you see a duck sitting on the pond with any waves at all, pay attention to it. It's actually kind of funny to really watch. So when waves interact, they can sort of build on top of each other. They're building their amplitudes. They're going to add or subtract. It's the summation of those amplitudes. And this is known as the superposition of waves. Superposition means that things can superimpose on top of each other or add on top of each other. We have two different types of interference. There is constructive interference, which occurs when wave displacements are in the same direction. So we have this wave here, wave A going to the right, wave B going to the left, and then when they meet right here in the middle, the two waves will add together. Since they're both in a positive direction above the midline, they will both add together and make a bigger wave, just in the moment when they're passing each other. Then once they've gone past each other, it's as if neither one was there and they just keep moving along their business. Kind of like people should do. So destructive interference is when you have one wave in a positive amplitude, one in a negative amplitude. Then when they meet, the entire thing will just go to nothing. It's as if nothing is there, at least if the two have equal amplitudes. If wave A was bigger than wave B, then you would still see some hump here in the positive direction. And again, once they go by each other, it's as if neither one was there in the first place. Constructive interference versus destructive interference, one is not necessarily good or bad. It's just dependent on what you want. So if you have constructive interference can be good for an instrument because you want resonance to occur and you want the sound to be louder. With other things, you want destructive interference because you don't want waves to build up in certain objects. So if you have a structural object, we would want that to be destructive interference. And I'll see if I can find an example for it. So here's an example of what's known as the Galloping Girdle, the Tacoma Narrows Bridge collapse that occurred back, I think, in the 40s. Don't quote me on that quite just yet. But so this is a classical example of constructive interference occurring on a bridge. Now, since then, they've actually explained it in a different way, but I'll still go about it because it'll work out fine. So if you watch the video, this is a really old video of this bridge, the suspension bridge. You can see how there's this torsional twist, this constructive interference that occurred because of a high wind day and caused this bridge to sway to the point to where if you can imagine a kid on a swing. If you were to just push a child randomly at random intervals while, you can see the man trying to stand on this bridge, but if you were to push a child on a swing at random intervals, so you just close your eyes and you just like push your arms out to push them randomly, you're going to wind up pushing the kid off the swing. If you're pushing your hands outward when they're still coming back towards you, that would be kind of mean. Constructive interference is when you are timing it just right to where when you push your arms out, the child is starting to move away from you again. And so that would be sort of an example of constructive interference. Okay, so let's go back to our little PowerPoint here. Okay, so that depends on whether you want constructive or destructive interference. Either one can occur. So question one, what kind of interference occurs to make a wave bigger? Constructive interference would be the answer. Yes, I'm sure you said that to yourself. Wave velocity. So the velocity of a wave is going to be its wavelength, measured in meters, divided by the time it takes for each wave, measured in seconds. So it's meters per second. Since t is equal to 1 over f, you can also express that wave velocity as the wavelength times the frequency. So if you notice here, this symbol is known as the lambda symbol. Okay, that is the symbol for wavelength. This sort of italicized f is the symbol for frequency. So in standing waves, we have some different parts of a standing wave. And so let's look at what a standing wave actually is. I'm going to bring up a video here. or actually a little animation, so I'll start this animation. So here we have an onset wave that's coming in from the left, and the positive, or excuse me, the red refers to the initial onset wave, this wave that's coming in from the left. Let's imagine somebody has a rope and the person's moving their hand down, and then they're starting to move their hand back up, and so on. And so this red part here is due to that person's hand moving the rope up and down. Then it's going to hit this barrier here, and it's a fixed barrier, so it's going to reflect. Watch how it reflects to the other side. The blue represents the reflected wave. This part here, and you can see this part going up right here, this is the addition of the two waves. That is what you would actually observe happening in the string. This is what you would actually see the string doing. And as the reflected wave interferes with the initial onset wave, you get this constructive interference. And in fact, if you get the tension just right in the string, you'll have these points here that have no movement at all. Those are known as nodes, no movement. The spots that have lots of movement, it just keeps right at the same spot, always in the same spot. You have the same large amount of movement that is known as an antinode. And so you have antinodes here, lots of movement, nodes, spots of no movement. Okay? And let's see if we can show a... Oh, nope, same thing. Okay, that's okay. But so antinodes, the points of maximum displacement, a node, a point of minimum or no movement. And so a standing wave occurs when these antinodes and nodes stay in the same place. Resonance is essentially what happens within an object that has a standing wave. So for example, if you had a crystal glass and you flicked the crystal glass or rub your finger across the top of the crystal glass and get it to make that sound, that it is going to resonate. It's going to resonate at its natural resonant frequency. So resonance occurs within an object, and it occurs when you have a standing wave within that object. So resonance is just the name for a standing wave occurring within an object. So here we have these waves that are being produced from point sources. So this speaker, for example, is producing these waves in the darker blue, okay? And then this speaker is producing these waves with the lighter blue. Both speakers are producing the exact same frequency, and they're separated by some distance, d. Let's just say that it's a small distance. You notice that here you have two wave crests hitting on top of each other. And same here, and here, and here, and so on. And so what's going to happen is you're going to get a line right here of constructive interference. In fact, this is going to be known as an antinodal line. Then, if you notice right here, you have the crest of the blue wave at the trough of the light blue wave, and then you have the same thing here, and here, and here at point D. And so right here, you're going to have a nodal line. In fact, if you were standing at point D at this specific frequency, you would not hear the sound at all. I know that seems strange, but you would not hear that sound, versus somebody standing here would hear the sound very loudly. You, in fact, can have two people standing right next to each other where one person does not hear the sound and the other person does. That really can happen. The thing is that you have to be in just the right spots, and it has to be just the right frequency with these things at just the right location. The closer these two speakers are to one another, the more likely this is to happen. That's why you want to have your speakers set up a good distance away. You want them in the corners of the room to prevent that from happening. So that is two-dimensional wave interference. So let's look at sound specifically a little bit. The speed of sound in air is about 343 meters per second, give or take, depending on the temperature and humidity. The higher the temperature, the faster the speed. The higher humidity, the faster the speed. If you notice the speed in different objects, it is different. So in water, for example, the speed of sound in water is very, very high. The speed of sound in iron or steel is extremely high, which is why in old movies you might see, like old westerns, you might see somebody putting their ear to the railroad tracks to hear the train coming from some long distance away. Because not only does the sound travel faster in iron, but because it's traveling faster, it doesn't dissipate as quickly. And in fact, the same thing happens in air. When you have very humid days, the sound will travel faster and it will travel farther and better without dissipation. That's why after it rains, you might hear the birds chirping a little bit more loudly. Not only is it because they're actually out chirping, but also because the sound, with it being so humid out, the sound travels much better. So question 2, what do you call the spot on a standing wave with no movement or minimum movement? And if you remember, that spot is called a node. Okay, so interference of sound waves and beats specifically. So here we have a wave in pink that is at 50 hertz, and then we have another wave here in blue that is at 60 hertz. So when the two waves are layered atop of each other and superimposed on top of each other, let's say you have one instrument being played at 50 hertz and another instrument being played at 60 hertz, you will have a beat being produced. So if you notice right here, this is when the two waves are just lined up exactly right, and it's going to make a bigger wave because it's constructive interference. But over here, the two waves are exactly opposite of each other. They're 180 degrees out of phase with each other. And so one is in the positive, one is in the negative, and they'll cancel each other out. And in fact, you will not hear any sound at all. So what you'll hear is you'll hear the sound of these instruments getting louder and quieter 10 times per second. 10 times because that's the difference between their two frequencies. So that's why if you're in band, you'll know that it's so important to tune your instrument, because if someone else is trying to play the same note, but they are playing the same note, let's say 2 hertz off, you're going to hear 2 times per second this sound, this whoa, 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 whoa. You're going to hear this very strange and generally unpleasant sound of a beat being produced. So that's what a technical term is for a beat, which is why I'm really good at dropping them. So let's look at some visual demonstrations of what a beat is. Let's see if I can get to this here. And so here we have these two frequencies. One's 250 and one's 257. And I'm going to overlay the two waves. So right here, they're perfectly lined up. And then as we go over here, they're starting to get misaligned. So let's kind of zoom out just a little bit, and you can see that a little bit better. That over here, they're exactly misaligned, so there's no volume that you would be hearing. And over here, they're perfectly lined up, and you'd be at maximum volume. So you would be hearing, because the difference is 7, you'd be hearing 7 beats per second. It would be getting louder and quieter 7 times per second. If you have two tuning forks, and if one is off by the other by 1 hertz, it's a very strange sensation, because you're going to hear it go, ooh, ooh, right? In fact, I'm not even doing it right because I'm changing pitch, and it's not a change in pitch, it's a change in volume. But I think you kind of get the idea. Okay, so let's move along and try and keep this as short as I can. Oh, there actually is another little clip I want to go to there. So let's see if I can do that real quickly. I lost my spot. There we go. All right. Here we go. So here's just another little visual. So here's these two waves. One is, relatively speaking, this is the relative speed. So one's 400 and then one's 401. And so you can see over here that 1 time per second, you would see the addition, or, the amplitudes are getting larger and smaller 1 time per second. Okay? Okay. Frequencies within the auditory range. So this is just our perception. Our ability to hear is between 20 and 20,000 hertz. So 20 times per second. Anything below that, you're not actually going to be able to hear it. Not if it's a true 20 hertz. If something tries to move back and forth 10 times per second, if there isn't any other additional vibrations, you won't hear it. So a speaker diaphragm moving back and forth 10 times per second, you theoretically shouldn't hear it. In truth, though, when it's trying to move back and forth 10 times per second, the speaker moves out and it stops. And when it stops, it's going to wind up kind of vibrating the diaphragm a little bit, and it has its own natural resonant frequency, so it's hard to actually produce. There are some very special fan-based subwoofers that are able to produce low frequencies, and it's very strange because one person can hear it and the other person can't, because not everybody, it's not exact for everybody. It's not like, oh, at 20 hertz, everybody can hear it, and at 19, everybody can't. It doesn't work that way. So, for example, I can hear a little bit below 20 hertz, it's just because I'm a freak, and so I know that I have that ability. For the high end, though, my ability tops out at around, I think, 15,500 hertz, so much lower than 20,000. That's because I'm a little bit older. So as I get older, each year that goes by, and I've noticed it, that my ability to hear the high frequencies diminishes. At 17 years old, you're probably at about 18,500 hertz, give or take. When you're born, it's 20,000. If you're 80 years old, your grandpa might only be able to hear about 8,000 hertz. Yes, 8. And in fact, the truth is sometimes if you have someone who has a high-pitched voice, an older person sometimes can't hear what they're saying very well, and that's actually part of the reason why. Part of it might be they just kind of don't want to. Power and intensity of sound versus decibels. So right around 100 hertz is where hearing damage starts to occur, and that is why you do not want to listen to loud music. As you listen to loud music, your ability to hear this high range actually goes away. There's these small fibers in your inner ear that break with loud sounds. So power and loudness is not exactly the same. You see, in fact, I'm just going to focus on this. The intensity is the power, and as you increase your distance away from an object, the intensity diminishes exponentially. However, your ability to hear is actually more in line with the logarithmic scale. So an increase in sound level of 3 decibels is actually doubling the intensity. So your ability to hear actually goes more along the lines of that decibel scale. Strings of a guitar, you can shorten the string effectively, and it's going to increase the pitch. The velocity of the wave isn't going to change, but the pitch will change because you're shortening the wavelength and increasing the frequency. With wind instruments, here you have an open end of an instrument and a closed end, and it has a special type of wave that produces. So we'll take a look at that in a second. The fundamental is the simplest wave possible that can be made within an instrument, and the harmonics are the next subsequent waves that can be made. So the first harmonic is the fundamental, and the second harmonic is the next more complex wave. The first harmonic has 1 antinode, the second harmonic has 2 antinodes, and etc. So let's look at a wind instrument that has 2 open ends. So if you just had a pipe, for example, that had 2 open ends, and you were to force sound into this pipe and get it to resonate, you would have an antinode at each end, open end of the pipe, because the open end does not force any sort of reflection. You can go ahead and ignore the portion on the right here. So if you notice here, in this case, the length of the pipe is the same as the length of the wavelength. Let's say that this is the onset wave. Here is the onset wave. Okay, we're just focused on this one. And then this up here is the reflection of the wave. Okay, so this is the onset wave, and then the reflection. So look at the onset wave. It's at the bottom on its way moving up, and then it's on the bottom on its way moving up. So this is one complete wavelength, and this is the second harmonic, and then third harmonic, and so on. And you can see that this has 2 complete antinodes, 1 complete one in the middle, and half here and half there. That's the second harmonic. If you have something that has a closed end on one side and an open end on the other, you're going to have a node at the closed end because it's forcing a reflection. Here you have a wave being onset, and then it reflects, and this is the reflection. So this is the fundamental. Notice that only 1/4 of the wave is actually in the tube. The next harmonic, onset wave, reflects, crosses, and then antinode at the open end, and then the next harmonic. And yes, we are technically skipping. I'm not going to really get into that too much, but basically it's because you don't have a complete antinode. So this is for an instrument that has one closed end and one open end, and that's kind of how most instruments are. We have an experiment that we like to do where there is one closed end and one end open end of the tube. So open end is on the top, and the closed end, it occurs where there's the water. So we put this tube in and out of a column of water, and when the sound being projected in by a tuning fork, so the sound is forced its way in from a tuning fork into the tube, the sound reflects off the surface of the water and bounces back. And what you have is here you have a node because it's being forced backward into a reflection, and then an antinode at the top. And so the fundamental would have only 1/4 of the wave is in the tube. And then at the next one, you would have 3/4 of the wave in the tube. You can imagine here, right? So the entire wave is going to extend out and above the tube a little bit. And so 3/4. So here's 1, 2, 3/4 of the wave would be actually in the tube, and then the rest of the wave actually makes its way out of the tube. You can imagine the next node being out of the tube. So here's a question. The length of the ear canal is 2.4 centimeters. What is the resonant frequency? Let's treat the speed of sound to be 343, not the 345, but 343 meters per second. The auditory canal is 2.4 centimeters long. This is the closed end of essentially a pipe, and this is the open end of a pipe. So what is the resonant frequency, the fundamental resonant frequency of the auditory canal? All right, so let's take a quick look at this. Let's pretend that this is your auditory canal. This is your eardrum, and this is the open end of your ear. So the fundamental is going to look like this, where you have wave coming in. There's the node and the reflection there. I'll switch colors to show you the reflection. Okay, and then the reflection is going to come out something like this, and then there's going to be the antinode here and a node here. So 1/4 of the wave is actually in the tube, and I'll kind of dotted line draw the rest for you so you can see that. I'll do the dotted line for the other side as well. I know it's not the prettiest thing, I'm sorry. And so let's take a look to see what is the where is the full wave. So let's just look at the onset, the blue. Right, this right here is one complete wave. Okay, so right here, that's where there's a complete wave. Notice that 1/4 of it, so 1, 2, 3, that's 4/4. 1/4 of it is actually in the tube. So if 1/4 of it is in the tube, you have to multiply this length of the tube, which is, remember, 2.4 centimeters. That's your auditory canal. You're going to multiply that by the reciprocal of 1/4, which is 4 over 1, or 4. So if we were to take 2.4 times 4, that'll give us, what, 9.6 centimeters. But of course, we have to be in meters. So that's 0.096 meters. Since velocity is equal to wavelength times frequency, if I want to find the resonant frequency, I'm going to divide each side by wavelength. So velocity over wavelength is equal to the frequency. So that means, let's see, we've got 343 meters per second over a wavelength of, we said, 0.096 meters. Meters will cancel out, and I'm going to be left with cycles per second because seconds is in the denominator. So if we want to actually find that value, then we're going to say 343 divided by 0.096. And I already have that done. So 3573. So 3,573 cycles per second, otherwise known as hertz. Now keep in mind, this is only the fundamental frequency. The next frequency would occur when you have 3/4 of the wave in there. Let's see if I can use another color to draw that right on top. That does not look pretty, but I think you get the idea, where there's an antinode at the open end and a node here and then a node somewhere in between. And there would be another fundamental, another harmonic. That'd be the second harmonic, actually technically the third. And then there's another one. So there's actually three frequencies that can resonate inside the auditory canal, which is why some frequencies, this one in particular, hurt. It hurts. I can't make this stuff up. So it actually sounds louder at that frequency because it's resonating within your auditory canal. Let's get back to where we were, and we'll just kind of get to wrapping this stuff up. Let's look at Doppler effect, which is pretty interesting. If you guys know what the Doppler effect is, a car goes by you and it goes wrong. So let's look at what happens. So this is a wave that is being produced from a point source, and then this is from a point source that is moving from our left to our right. So if you notice that if you are in front of this object and it's coming towards you, then the waves are going to be closer together because the object produces a wave and then it tries to catch up to that wave and it produces yet another one. And so the wavelength is shorter, so the pitch is higher. If wavelength is low, then pitch is high. If you're behind it, it's the opposite, so the wavelength is going to be a little longer. And then if the object actually moves at the speed of sound, in this case if it's sound, they're going to have a sonic boom, which is awesome to see in person, trust me, because it looks like that. So if I've been able to go to 2 different air shows where I was able to see that happen in person. This happens because the air is actually being compressed so much along that leading edge that it actually pushes all the moisture right out of the air. And in fact, there's a cone at the front and a cone at the back because there's one sonic boom from the nose cone and another sonic boom from the tail. So 2 shock waves is what you'll actually get from it. Let's look at what reflection is. So reflection occurs when a wave comes in, hits a surface, and then reflects to the other side. This dotted line represents the normal. Remember, the normal is perpendicular to the surface. So the law of reflection states that the onset wave and the reflected wave will have the same angle relative to the normal. So here's just another picture of it. Here's the incident ray. Here's the reflected ray. And those 2 angles relative to the normal will be the same. That is the law of reflection. Here is refraction. Refraction is different. Refraction occurs due to a speed change. So for example, when light goes from air into water, it will move slower in water than it does in air. And so it will bend towards the normal. If you can imagine, let's say a series of people walking in row, like a marching band, and they're going from concrete. Let's just imagine this is concrete and down here this is mud. So we have a group of people side by side walking, and they hit the mud. The people that are on this side are going to hit the mud first, and they slow down first. This group of people would wind up turning towards the normal in this case until they're all in the mud. Or if you can imagine like a track vehicle, like a tank or something, where the track that is on this side would hit the mud first, and it would start to slip, and it would turn as it's entering the mud. It would turn towards the normal. So it has refraction. It would happen in the opposite direction, going the other way. So going from slow to fast moving medium, the light ray would actually bend away from the normal. Here's a fun little image. So I know it looks pretty weird, but here you got this really cool guy, because he likes physics. So his body is directly below his head, but what's happening is the light is coming out into the direction towards the glass, and then because it's going from a slow to fast moving medium and going from the water to the air, it is going to bend away from the normal, away from the surface of the glass, and it's going to come towards your view, towards the camera. And so that's why this is produced. Diffraction is the spreading of a wave around or through a barrier. So here, it spreads around this outer leading edge of this barrier, and just like any sound would try and spread out, it's always trying to spread out around the barrier. So it turns out that longer wavelengths will spread more. Okay, longer wavelengths spread more, which is why if you are going to a football game and you're approaching the stadium, you're going to hear the low frequency sounds first as you get closer and closer. So you're going to hear the tubas and the drums because longer wavelengths can diffract more, go around the stadium, and you're going to hear them better. Also, the diffraction through gaps. If you have a narrow gap versus a wide gap, there's going to be more diffraction, more spreading of the wave through a narrow gap. So if you were to have, let's say, a laser beam, if you do have a laser beam, give this a try. It's kind of neat. Take a laser, shine it on the wall, you're just going to see a dot on the wall. But then take a couple of playing cards or something like that have very nice sharp edges to them, and put the two playing cards just impossibly close to each other, and shine a laser beam through the tiny gap of the two playing cards. And if you can get the gap just right, you'll actually see a line develop on the wall rather than just a dot, because the wave will spread as it goes past that barrier. Because the light has such a small wavelength, though, you need a very, very small gap in order to produce any noticeable diffraction. All right, I know that was a lot, but that actually is going to do it for waves and sound. So that is my entire lecture for the most part on that section and on that unit. Okay, so hopefully that was good. Let me know if you guys have questions. You guys take care.